factor F12 in a cylindrical cavity of diameter d and height h between the bottom face known as surface 1 and the top flat surface known as surface 2. This is a problem on shape factors. The figure is given like this. This is the diameter d. This is height h. This is all considered as surface 1, entire bottom one, whereas this is considered as surface 2, top one. This is top one is considered as surface 2, bottom one is considered as surface 1. So here one surface is totally enclosed by outer one. The solution could be given like this. Here surface 2 is totally encircled or encompassed or surrounded. Here surface 2 is totally surrounded by surface 1. I told you already, when one surface is completely surrounded by outer surface, shape factor of the inner surface with respect to the outer is equal to unity. Therefore, shape factor F21 is equal to 1. From reciprocity relation, A1 F12 is equal to A2 F21 implies F12 is equal to A2 by A1 into F21. What is A2? Pi by 4 d square, that is circular area of the top flat surface. What is A1? Pi by 4 d square plus pi dh into 1. F21 is 1. It becomes pi by 4, you can pi could be cancelled. First of all, pi could be cancelled. It becomes 4d by d square by 4 divided by d square plus dh by 4. dh d square by d square plus 4 dh. This is the answer. Next problem on shape factors. A hemispherical surface 1 lies over a horizontal plane surface 2 such that convex portion of the hemisphere is facing sky. What is the value of the geometrical shape factor F12? The figure is given like this. This is surface 2. This is surface 1. Radius of the hemisphere is R. The answers are A 1 by 4, 1 by 2, 3 by 4, 1 by 8. The solution could be given like this. Here surface 2 is totally enclosed by surface 1. Hence F21 is equal to 1. From reciprocity relation, A1 F212 is equal to A2 F21. Therefore, F122 is equal to A2 by A1 into F21. That is A2 by A1 into F21 is equal to 1. What is A2? Pi r square. What is A1? 2 pi r square. That is surface area of the hemisphere. Answer is 1 by 2. B. Next problem on radiation. Two spheres A and B of same material have radii 1 meter and 4 meter and temperatures 4000 K and 2000 K respectively. Which one of the following statements is correct? The energy radiated by sphere A is A greater than that of sphere B, B less than that of sphere B, C equal to that of sphere B, D equal to double that of sphere B. Here the two spheres are made of the same material. The total energy radiated emitted from sphere is equal to E into A. It could be written as epsilon into EB into A. That is epsilon into sigma T to the power of 4 into 4 pi r square, where T is the temperature and R is the radii. Therefore, energy emitted from A divided by Q emitted from B is equal to epsilon of A sigma TA to the power of 4 pi RA square divided by epsilon of B sigma TB to the power of 4 into 4 pi RB square. Epsilon, because they being same, they made of the same material, therefore results in what is the temperature of the A? 4000 to the power of 4, 4000 by 2000 whole to the power of 4 into what is RA? 1 by 4 whole square, that is 4 by 2 to the power of 4 is 16 divided by 4 square is 16, 1 equal to that of sphere B. C is the answer. A will emit the same energy as that of the B because the ratios being 1. Now I shall deal with the radiation heat exchange between two infinitely long parallel gray, diffusively gray, more correctly, all the surfaces what we deal are assumed to be diffuse, they are not specular. What do you mean by diffuse surface? Intensity of radiation is independent of the direction. I consider two infinitely long parallel gray surfaces having emissivities epsilon 1, epsilon 2. This is surface 1, this is surface 2. Please note that surface 1 is looking at surface 2 and vice versa. The backside surfaces are not involved in the radiation heat exchange problem. The surface 1 is having the temperature T1K. Let T1 is equal to absolute temperature of surface 1 and T2 is equal to absolute temperature of surface 2. Epsilon 1 and epsilon 2 are their emissivities. Then T1 is assumed to be greater than T1. Then net radiation heat exchange between 1 and 2 is equal to Q1 to 2 net is equal to sigma T1 power 4 minus T to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1 per unit area. This is, note that you have considered per unit area, that is heat flux. We can also call it as the heat flux. Net radiation heat flux exchange between 1 and 2 is given by this formula, so many watts per meter square, where sigma is the Stephen-Boltzmann constant. This is a net radiation heat exchange per unit area between two infinitely long parallel gray surfaces. Now I shall deal with radiation heat exchange between two infinitely long concentric cylinders. Radiation heat exchange between two infinitely long concentric cylindrical gray surfaces. Radiation heat exchange between two infinitely long concentric cylindrical gray surfaces. The surfaces are shown in the figure. They are concentric, axis is same. The outside surface of the inner cylinder and the inside surface of the outer cylinder are exchanging heat by radiation. This is R1, this is R2. Let epsilon 1 and epsilon 2 be the emissivities of inner and outer surfaces respectively, and T1 and T2 be the absolute temperatures of the surfaces in Kelvin. Epsilon 1 be the emissivity of the inner surface, epsilon 2 be the emissivity of the outer surface. T1 Kelvin be the temperature of the inner surface, T2 Kelvin be the temperature of the outer surface. R1 and R2 be their radii. Inside surface is treated as 1, outside surface is treated as 2. If you look at the side view, the side view is given like this. From the side view, whatever the energy that is leaving surface 1 is intercepted by the surface 2, because they are very, very long concentric cylinders. Whatever the energy that is leaving surface 1 has to be intercepted by the surface 2. Therefore, shape factor of 1 with respect to 2 is 1. Since all the energy, radiation energy leaving surface 1 is intercepted by surface 2. But F21 is less than 1. Since only a part of the energy leaving surface 2 is intercepted by 1, and the remaining energy will be going towards the same surface 2. So F21 is less than 1. Only a part of the energy leaving surface 2 is intercepted by the surface 1, and the remaining balance energy will go towards the same surface 2. In such case, net radiation heat exchange between surface 1 and 2 is Q net is equal to sigma T1 to the power of 4 minus T to the power of 4 divided by 1 by epsilon 1 plus A1 by A2 into 1 by epsilon 2 minus 1 into A1. So many watts. This is very important formula. So many watts. This is very important formula because it is applicable to all the cases of radiation heat exchange whenever one shape factor is equal to unity and the other shape factor is less than unity. I give some examples here. The various examples for this case are, that is, when one body is completely surrounded by another. I consider two concentric spherical surfaces shown in figure. This is surface 1, this is surface 2. Epsilon 1, epsilon 2, T1, T2. That is, the outside surface of the inner sphere is exchanging heat by radiation with the inner surface of the outside sphere. T1 is greater than T2. Therefore, F12 here is equal to 1. But F21 is less than 1. And also, F21 is equal to A1 by A2 from reciprocity relation. Reciprocal relation also known as 4 pi R1 square, where R1 is the radius of the inner sphere, R2 is the radius of the outer sphere. 4 pi R2 square, that is R1 by R2 whole square. Therefore, Q12 here could be written as sigma T1 power 4 minus T to the power of 4 into A1, where A1 is given by 4 pi R1 square divided by 1 by epsilon 1 plus R1 by R2 whole square into 1 by epsilon 2 minus 1. So many watts. Now another example is when another example when a small body is kept in a large enclosure. A small body is there of surface area A. When it is kept with a large enclosure, small body is taken as 1, large enclosure is taken as 2. Body is 1, considered as surface 1, enclosure is 2. Here, since 1 is totally surrounded by surface 2, F12 is equal to 1. Hence, that formula could be written. Therefore, Q122 is equal to sigma T1 power 4 minus T to the power of 4 divided by 1 by epsilon 1 plus A1 by A2 into here A1 is 2 lesser than A2, implies A1 by A2 ratio tends to 0. In such case, Q12 net radiation heat exchange is given by sigma T1 power 4 minus T to the power of 4 into A1 into epsilon 1. So many watts. This is a net radiation heat exchange by the small body kept in a large enclosure. I consider another example. Consider a fluorescent lamp, electric lamp of wattage, say 60 watts, in a room. Now it is required to calculate surface area of tungsten filament in the bulb or temperature of filament given ambient or surrounding temperature. There is a bulb, 60 watt bulb. So in each second 60 joules per second of energy is being radiated. It has got tungsten filament. Ambient is taken as T infinity. Kelvin. Let Tf be the temperature of the filament. In Kelvin, and let A be the surface area of filament. Then under steady state conditions, Q is equal to radiation heat exchange between filament and ambient surroundings, neglecting glass surface. We are not considering the influence of gas surface. We are taking the filament as surface 1, ambient temperature as surface 2. So here F12 is equal to 1. Also A1 is far lesser than A2 because filament area is almost negligible as compared to the surrounding ambient surface area. Ambient means all the room, etc., which is at a temperature of T infinity Kelvin. Therefore, Q net radiation heat exchange between filament to ambient is nothing but wattage. I suppose 60 watt bulb. This is equal to sigma into temperature of the filament to the power of 4, temperature of the ambient to the power of 4 into epsilon of the filament into surface area of the filament. So in this equation, sigma is, pretty well 5.67 into 10 power minus 8 watts per meter square Kelvin to the power of 4. So if there in this equation, if epsilon of the filament is also given. So any one unknown, either surface area of the filament or temperature of the filament may be calculated given the wattage of bulb. So this is one of the examples taken when one body is completely surrounded by another body.